Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked from the GATE Physics paper 2021. This is a MCQ type 2 marks question, and this question was asked from the topic quantum mechanics. The question is, consider a state described by psi as a function of x and t equals to psi 2 plus psi 4, where psi 2 as a function of x and t and psi 4 are respectively the second and fourth normalized harmonic oscillator wave functions, and omega is the angular frequency of the harmonic oscillator. The wave function psi as a function of x and at time t is equal to 0 will be orthogonal to psi as a function of x and t at time t equal to 4 options are given. Option A is pi by 2 omega, option B pi by omega, option C pi by 4 omega, and the last option, option D, pi by 6 omega. So we have to choose the correct answer from these 4 options. Let us see how to solve this problem. It is given in the question that our wave function psi as a function of x and t is basically linear combination or superposition of two different state harmonic oscillator wave function. Those are psi 2 and psi 4. Here psi 2 is the second, that is the n equals to 2 state normalized harmonic oscillator wave function, and psi 4 is the fourth, that is at n equals to 4 state normalized harmonic oscillator wave function. Now for a one-dimensional harmonic oscillator problem, the energy of the nth eigenstate is given by En equals to n plus half h cut omega, where omega is the angular frequency of the harmonic oscillator and n defines the state of the harmonic oscillator. Here n can take the values 0 or any positive integer values. Now harmonic oscillator potential energy is time independent. So for this case the wave functions will be stationary state for the harmonic oscillator problem. This means at any time t, we can write the time evolution of any harmonic oscillator wave function, that is psi in as a function of x and t equals to multiplication of two independent functions, and first function is basically the wave function at t is equal to 0 times one exponential term, that is e to the power minus I ent by h cut. So this exponential time dependent term basically describes the time evolution of the harmonic oscillator wave function. Here En is the energy of the harmonic oscillator state at nth state. So we'll apply the definition of the stationary state in our case. So our wave function psi as a function of x and t equals to psi 2 times e to the power minus I2 t by h cut plus psi 4 e to the power minus I e4 t by h cut. Here psi 2 represents the wave function psi 2 at t is equal to 0, and psi 4 is the wave function at psi 4 at t is equal to 0. Now if the wave function psi at t is equal to 0 is orthogonal to the wave function psi at any time t, then we can write the inner product between these two wave functions is 0. Now at t is equal to 0, basically the wave function psi is psi 2 plus psi 4. So we'll write this psi as a function of x and t is equal to 0 is psi 2 plus psi 4, and psi as a function of x and t is given by this. So we'll write that here. Then we'll multiply this psi 2 with this 2 term and psi 4 with this 2 term, and we'll expand this. So we'll get 4 terms from here. So first term will be the inner product between the psi2 and psi2 multiplied with the exponential term, and second term will be inner product between psi2 and psi4 and this exponential term containing the energy term E4, and third term will be the inner product between psi4 and psi2, and the last term will be inner product between psi4 and psi4, and also multiplied with the energy, the time evolution part. Now the wave functions psi1, psi2, psi3 and so on, they represents the normalized wave function for the harmonic oscillator, and they are orthogonal to each other. This means the inner product between the same wave function will be 1, but inner product between the two different wave function will be 0. This means our inner product between psi2 will be 1 or psi4 will be 1, but the inner product between psi2 and psi4 or inner product between psi4 and psi2 will be 0. So because of this, if we remember the last equation, in that only two terms will survive, which contains the inner product between psi2 and psi2 and inner product between psi4 and psi4, and rest of the terms will be 0, and that will give e to the power minus I e2t by h cut plus e to the power minus I e4t by h cut equals to 0. Now we'll divide the whole part by e to the power minus I e4t by h cut. So basically it will give e to the power I e4 minus e2t by h cut plus 1. So we'll take that plus 1 at the right hand side. So it will give this equation. Now from the complex number theory, we know e to the power I pi is basically minus 1. So we'll write this minus 1 as e to the power I pi. Now comparing the exponent part, we can write basically e4 minus e2 times t by h cut equals to pi. From the last equation, we can write the time t equals to h cut pi divided by e4 minus e2, where E4 is the energy of the harmonic oscillator at n equals to 4 state and E2 is the energy at n equals to 2 state. Now we have already seen the energy of the harmonic oscillator at nth state is n plus half h cut omega. So we'll apply that formula and we can write E4 minus E2 as 4 plus half h cut omega minus 2 plus half h cut omega. So this will give E4 minus E2 equals to 2 h cut omega. So we'll put this in this equation. So we'll get t equals to h cut pi divided by 2 h cut omega. So h cut and h cut will be cut from the numerator and denominator, and we'll get our time t equals to pi by 2 omega. So this time at this time pi by 2 omega, basically the wave function psi at t is equal to 0 will be orthogonal to the wave function psi as a function of x and t. So this t equals to pi by 2 omega, that is the option A, is the correct answer for this question. So according to our solution, the wave function psi as a function of x and at time t is equal to 0 will be orthogonal to psi as a function of x and t at time t equal to option A, pi by 2 omega. So option A is the correct answer for this question. This question was asked in the GATE Physics paper 2021. This is a numerical answer type 2 marks question, and this question was asked from the topic quantum mechanics. The question is, the normalized radial wave function of the second excited state of hydrogen atom is r as a function of small r equals to 1 by root over 24 e to the power minus 3 by 2 times r by small a times e to the power minus r by 2a, where a is the Bohr radius and small r is the distance from the center of the atom. the distance at which the electron is most likely to be found is y times small a. The value of y in integer is, so basically you have to find the value of y such that the electron is most likely to be found at the distance y times a, where a is the Bohr radius. So let us see how to solve this problem. The general form of the hydrogen atom wave function is given by psi nlm as a function of r theta phi in spherical polar coordinate equals to multiplication of two function. First function is rnl as a function of small r, which is radial distance. So basically this function is radial part of the wave function, and the other function is ylm as a function of theta and phi. So this is known as spherical harmonics, which contains the angular information of the wave function. Here n is the principal quantum number, which can take the values 1, 2, 3 and so on. The L is orbital quantum number. Depending on the n value, it can take the values 0, 1, 2 up to n minus 1. And the m is magnetic quantum number, which is represented as ml because its value depends on the L value, and the values it can take, ml equals to minus L plus 1 and so on. It can take maximum value up to L. Now we will discuss about the normalization condition for the hydrogen atom wave function. According to the normalization condition, the integration over entire volume, that is integration over r, theta and phi of the wave function mod square times the elemental volume, that is r square sine theta d theta dr d phi equals to 1. Now this wave function psi nlm is multiplication of two part, that is radial part rnl and the angular part which is spherical harmonics, that is ylm. So we'll put that, we'll get integration over r theta and phi mod of rnl square and mod of ylm square times r square sine theta dr d theta d phi equals to 1. Now we'll separate the radial part and the angular part in this integration. So we'll get integration from r equals to 0 to infinity of r nl mod square times r square dr, and the other part is the angular part, that is integration from theta equals to 0 to pi, integration over phi is equal to 0 to 2 pi mod of ylm square sine theta d theta d phi equals to 1. Now we'll concentrate on this radial part only. So here this term, that is mod of rnl square r square, this term is denoted by pnlr. So this pnlr, which is mod of rnl square and r square, is known as probability density function at radial distance r. So we will see why it is important in our case in the next slide. So the probability that the electron in hydrogen atom would be found between the radial distance small r and r plus dr is given by the probability density function, that is PNL as a function of r times the dr equals to the mod of RNL square, that is the radial part of the wave function, times r square times dr. Now in our question, the normalized radial wave function of the second excited state, that is the principal quantum number equals to 2 in this case of the hydrogen atom, is r as a function of small r equals to 1 by root over 24 times e to the power minus 3 by 2 r by e times e to the power minus r by 2e. Here is the Bohr radius. Now if we want to represent this radial part in the formal way, that is RNL form, so basically it will be R21 because it is the wave function for second excited state. So N will be 2 and L can take value either 0 or 1. Now we'll not discuss it much from the, I mean, we can only say here from the solution of the Schrodinger equation, we can get the R21 function is this. Now, the probability density function P21 in this case, mod of R as a function of small r square times r square, where r as a function of small r is given by this. We have to find the most probable value of small r, which is radial distance, or the value of small r, where the probability of finding the electron in the hydrogen atom is maximum. Now we'll consider the most probable value of r is Rm. So at r equals to Rm, the probability density function, that is P21 in our case, will be maximum. So at r equals to Rm, the derivative of the probability density function P21 with respect to small r will be 0. So we'll put the expression for P21 in this equation. Now P21 is basically mod of R21 square times R square. Now mod of R21 square is 1 by 24 times a to the power minus 3 r square by a square times e to the power minus r by e times r square, there is a term. And then we'll take these constant values, so that is 1 by 24 e to the power minus 3 and here 1 by e square out of this derivative. So effectively we'll get the derivative with respect to small r of r to the power 4 e to the power minus r by e at r equals to Rm equals to 0. So we'll just do the derivative here. So we'll get 4 Rm cube times e to the power minus Rm by a plus Rm to the power 4 times minus 1 by a times e to the power minus Rm by e equals to 0. So we have done the derivative of this function. Now we'll take this Rm to the power 3 times e to the power minus Rm by e as common, and remaining term will be 4 minus Rm by e. So from here we can conclude 4 minus Rm by e equals to 0, since the remaining part Rm whole cube times e to the power minus Rm by e not equals to 0, because Rm cannot be infinity or Rm cannot be 0. So electron cannot exist within the nucleus, so Rm cannot be 0 in this case. Also Rm cannot be infinity, it should have some finite value for having the most probable value of R. So from this equation we can say Rm equals to 4a. So the most probable value of R is Rm equals to 4a. So our y value in our question is y equals to 4. Now we'll discuss some important tricks to solve this question very easily. So the first point is, if the radial part of the hydrogen atom wave function is proportional to e to the power minus r by Na, then we can directly say the principal quantum number for the wave function is n. So in our case the wave function radial part was for the second excited state, so n equals to 2. Now if we know the principal quantum number for the wave function, so we can say directly the probability of the finding electron is maximum at Rm equals to n square e. So in our case n equals to 2, so the most probable value of Rm is 4a. So this shortcut formula we can apply to find the solution of this question. We have already solved this problem, and also we have discussed some important tricks which will be very useful to tackle this type of problem very easily. And we found that the answer of this numerical answer type question is 4. So the distance at which the electron is most likely to be found will be 4 times Bohr radius. This question was asked in the GATE Physics paper 2021. This is a MCQ type 1 mark question, and this question is from the topic solid state physics, specifically from the chapter dielectric properties of material. The question is, choose the graph that best describes the variation of dielectric constant epsilon r with temperature capital T in a ferroelectric material where Tc is the Curie temperature. So there are four graphs given. We have to identify the actual graph which describes the variation of dielectric constant of the ferroelectric material. So let us see the solution to get the proper graph for the ferroelectric material. Ferroelectricity is the state of spontaneous polarization in a material, that is, the polarization of the material in the absence of an electric field. So this ferroelectricity is analogous to ferromagnetic property of material or ferromagnetism, which represents the state of spontaneous magnetization in that ferromagnetic material. Now, the materials which exhibits ferroelectricity are known as ferroelectric materials or ferroelectric crystals. The examples of such materials are BaTiO3, that is barium titanate, K(PO4), that is potassium dihydrogen phosphate. There are some other materials also, etc. Now, the dielectric constant of ferroelectric materials varies as the temperature increases or decreases. The variation of dielectric constant with respect to the variation of temperature is described in the Curie law. So this Curie law depicts that the ferroelectricity disappears above a certain critical temperature known as transition temperature or the Curie temperature or Curie point, that is Tc. So mathematically, the Curie law says the dielectric constant depends on the temperature in this way, that is A by mod of T minus Tc, where A is constant, T is absolute temperature, and Tc is the Curie temperature, which is also known as phase transition temperature. So this temperature of the ferroelectric material, if it is less than Tc, then it is in ferroelectric state, and if it is greater than Tc, then it is in paraelectric state. So in the paraelectric state, as the temperature increases, the dielectric constant starts to decrease. Now we have already seen from the Curie law, the dielectric constant as a function of T for the ferroelectric materials is given by this. So here, if T greater than Tc, then the material is in paraelectric state, and if it is T less than Tc, then the material is in ferroelectric state. And T is equal to Tc is the phase transition from ferroelectric to paraelectric state. Now, if we plot this function, this epsilon r as a function of t, then first it will increase up to Tc. Then, if the temperature is greater than Tc, then it starts to decrease. So, our option A, the plot given in the option A, is the correct answer for this question. So, according to our solution, we found that the option A, that is the first graph, describes the variation of the dielectric constant epsilon r properly with temperature in a ferroelectric material, where Tc is the Curie temperature. So Tc is actually the phase transition temperature from ferroelectric phase to paraelectric phase.